मैथमेटिक्स कोऑर्डिनेट सिस्टम सबसे पहले कार्टेशियन। कार्टेशियन में हमारे पास पोजीशन वेक्टर को हम ऐसे लिखते हैं आर केप इक्वल टू एक्स आई केप वाई जे केप प्लस जेड के केप एंड द रिलेशन बिटवीन दिस डायरेक्शन is given by this, and the magnitude of r vector is given by simply x square plus y square plus z square, and this is because these all axes are at 90-degree angles with each other, so we can simply use Pythagoras theorem and have this ijk cape. These are constant vectors with time, means since it is unit vector it will not change magnitude and also it won't change direction. If I cape is pointing in that direction, then it will always point in that direction. I cape won't change to this direction or any other. It will remain in the same direction. That's what it means. Now displacement is given by delta r is equal to r final minus r initial. The final position minus initial position vector, or you can rearrange it, r initial vector plus r delta r vector is equal to r final. Elemental displacement. When the displacement is tending to zero, very small displacement, then we use this symbol dr, and it is given simply by this dxik plus dyjk. How do we get this? Simply through Pythagoras theorem, since we all know it. Let's skip this. And elemental distance, we got the displacement. Now distance, since the displacement is tending to zero, the x I cap we get, and when the element is very small, displacement element is very small, it becomes a straight line, and we get this I cap and this j cap vectors which tells the position. And since it is a straight line, we can use Pythagoras theorem and tell the magnitude of this length, distance, elemental distance. So that's how we get this, and for integration purpose we can change its form to this form. Divide by dx, we get this, and divide by dx and multiply by dx, so we get this. And this dr, we will also denote this dr by this sign dl, where dl means this length, the change in position. Dl is elementary change. Now moving ahead, we have polar 2D. We will only study 2D. In polar, the position vector is given by r vector is equal to r cap. So r is the magnitude of the distance from origin of the point P of the position we need to find, and the r cap is the direction to which it points, r vector. And there is another vector we need to know here, that is theta cap, a unit vector theta cap. Theta cap is a vector we take in a direction perpendicular to r cap. Now this is two possible direction, one in this direction and one is this direction. Now theta cap is taken in the direction in which the theta is increasing, or let's say the body is rotating in the direction or moving in the direction, then we will take theta in that direction. If the body is moving in that direction, then we will take theta in this direction perpendicular to r cap. Now r cap and theta cap are not constant with time, unlike ijk vector which were constant with time. They were not changing direction, but this r theta cap and r cap theta cap can change direction. If particle is at that point, theta r cap is in that direction. If particle is in that point, then r theta cap points in this direction. So direction can change if particle changes position, and it will remain constant if particle moves along the same line. Okay, now we will talk about that later. Now we have elemental displacement dr vector. So how do we find this equation? Let's derive. Okay, we get this coordinate system x, y, and here we have a particle at this position. Let's say the particle moves along this path. It has a r vector, and this is r cape, and this is the theta. This is the r vector. Now the particle, let's say, moves to this distance, a very small distance, which is a straight line. The change in angle is d theta, since it is a very small g. Now let's draw two circles. First with this radius r, the second one with a little change in radius. We will denote it by dr. Now there we got to know what is the use of this r sign, since dr means this length. So not get confused with this change in radius, we use this r sign here. I use this, you can use your sign. So here dr is the change in radius or distance of this from origin. So it denotes the change in distance or radius. So dr, and this is the length perpendicular. If we draw a circle about this final point, we get a radius, circle of radius r plus dr, and this is small length. Let's draw it here. Since this is a very small part of circle, this becomes a straight line, and it is at a 90-degree angle. Now this length is dr, and this length is dr. This length is r plus dr d theta. Since dr and d theta is small, we can take it equal to r d theta. Now there, since these two are perpendicular and this dr is pointing in r cape direction and this r d theta length is pointing in theta cape direction, we can say dr vector is equal to dr in r cape plus r d theta in theta cape direction. That's how we get this relation. And since these are perpendicular vectors, we get this relation. Now second thing and most important equations we need to learn is these two. Now we will derive this. Theta. We have x, y, these two. Now let's say there is a position r vector, and then there is r cape, there is theta cape. Let's say the angle is theta, this angle becomes theta. We can write this r cape vector equal to, this is I cape, this is j cape. So we get I cape cos theta plus j cape sin theta. This is equal to the r cape vector, and similarly we can write this theta cape vector. Theta cape vector is equal to, this is minus r I cape direction. So we can write it as minus I cape sin theta plus j cape cos theta. These are the unit vectors. Now let's differentiate with time. dr by dt, differentiating since it is a constant vector, we get I cap minus sine theta plus j cap cos theta. Differentiation of theta gives d theta by dt, which is omega, and the direction of omega is the direction of theta we chosen. So I chose the theta to be increasing in that direction. So omega is also in that direction. So it gives omega minus I cap sine theta plus j cap cos theta, and this is equal to this theta cap. So we can write it as omega theta cap. So dr by dt becomes equal to this omega theta cap. This is the first relation. Now deriving the second relation, differentiating the theta cap by dt. This will give y cap cos theta d theta by dt. Now this becomes, this is equal to r cap minus r cap, and this is become y. So here this relation minus omega r cap is what we derived here. So these two relations are important to learn. One thing to remember is r and r. This denotes the radius and change, and dr means change in radius, while r means position vector distance, and dr means the length, change in position vector's length, because it is. So don't get confused between those. dr is equal to dl, and maybe equal to dr. So remember this. Moving ahead, rotation of a vector. When a vector is of fixed magnitude, its magnitude is fixed and it is rotating with omega vector in any direction. So we will use polar here, just like we learned polar here. We will use that concept. We have, since magnitude of A is fixed, we want to find a change in a vector with respect to time. This can be written as dA cap upon dt times a vector magnitude. Since it is constant, magnitude is fixed. This is the vector pointing in the direction of a vector. Simply, it can be considered similar to position vector. And since it is rotating, we can say that it is equal to, formula we derived here was dr by dt is equal to omega theta cap. So we can write it as omega theta cap in the direction perpendicular to theta cap. And now this theta cap direction can be gained by, since object is rotating in that direction, we can say the omega is in upward direction. So omega cross a gives theta cap direction. So we can write it as omega cap cross a cap multiplied by magnitude of a and omega magnitude. This gives this rotation of vector, which is also written as this. So this is how we derive this relation dA by dt when the magnitude of position vector is fixed The rotation of a vector simply gives this value. In case of velocity, dv by dt, we get this equal to omega cross v cap, which is acceleration, and this is centripetal acceleration or normal acceleration. And when a position vector is rotating dr by dt, this gives velocity vector. Let's say the radius is fixed and it is rotating, then this gives omega cross r cap. Look, this is tangential velocity of the body in a circular path. So we quickly derived these relations using the relation before. Dr cap by dt is equal to omega theta cap. These are useful relations. Okay, moving ahead, we have some equations like v average. The speed average is given by distance traveled upon time taken. Instantaneous speed is given by the small distance, elementary distance divided by small time, and velocity average is given by the change in position vector r final minus r initial divided by time. So average velocity is the difference between average velocity and instantaneous velocity is that in instantaneous velocity we fix the point. Let's say the particle is going in that direction. In this way, we give we choose an initial position for average, and the change in position vector divided by time gives the average velocity. It can be any position change divided by time. We need an initial position for average velocity, while for instantaneous velocity the initial position is chosen exactly at the point where we want to find the velocity, instantaneous velocity. So if I want to find the instantaneous velocity at this point, then I will set my initial position at this point, and my final position will be just little bit after that. While in case of average velocity, my initial position is always at a starting point and final position can be at any point. So that's the difference between two. Now we get, this is the sign of average velocity denotation. It is a vector average, and velocity acceleration average is given by delta v by dt. Simple things. Similarly, instantaneous is given by dv by dt, and there is called jerk. I'm not a jerk. So jerk means the change in rate of change of acceleration, which is given by dA by dt. And now some other questions. Change in position vector, which is given by velocity vector into dt, and the change in velocity vector is given by acceleration integration with time, and the distance is given by speed integrate with time, and dv by dx is called velocity gradient. And these equations we remember as acceleration is equal to v dv by dx. So we can write this as this way in vector form. Or if you want to integrate along y-axis, then you use a y velocity in y direction, and if you want to use integrate along x direction, then you use velocity along x direction. How do you derive this? This is simple. Acceleration is equal to dv by dt. Now if I since I cannot multiply and I cannot divide by a vector, I simply take simple notion like dx by dt or dy by dt. Now this gives, so vx, dx by dt is vx, and we get dv by dx. That's how this becomes vx. If we want to integrate along y, make it dy by dy, and it becomes dy by dy, dy by dy. Okay, now moving ahead, the distance must be integrated. It cannot be taken from final initial positions, while displacement can be integrated and also can be directly found by initial and final positions. So, what is this magnitude? Rate of change of magnitude of velocity. Magnitude of velocity means speed. So, rate of change of speed is called tangential acceleration. We know that tangential acceleration changes the magnitude of velocity, while the normal or radial acceleration changes the direction. So the acceleration that changes the speed is tangential acceleration. And there is another thing which is magnitude of change in acceleration. So dv, velocity change in velocity vector, rate of change in velocity vector is acceleration vector, and taking the modulus gives the magnitude of velocity. So acceleration, so it is the magnitude of acceleration, while magnitude this is the magnitude of tangential acceleration. So both are different, and a total is given by a normal and a tangential. A tangential is given by this, a tangential or a per, so a tangential is given by this, the speed, rate of change of speed along the direction of velocity. This is the tangential acceleration, and the perpendicular or normal acceleration is given by this formula v square by rc. The direction is radial, and it can also be given by this v cross, the cross v, which we read before. When a vector is rotating, the rate of change of a vector is given by this formula. Now average is taken in two ways. One is time variance, the another is percent. We can find average with any variable, any x, y, z, w, a, b, c, d, anything. We just need to integrate the variable with that thing we want to take average with, putting the limits and the change in limits से divide करेंगे. Now we have, similarly, for if we want to find with position address, we will replace with this t with x, and if we want to find with any another variable, let's say a, then we will put a instead of t or x. Simple. Now omega vector, omega vector of a point with respect to another point. So whenever we find omega, how do we find omega? Omega vector is found by the line joining the 2 points. So if a particle is moving in a space, a point particle, we cannot tell the, if a point particle is moving in the space, we cannot tell the omega of it if we don't consider any other point. If we consider another point and the line joining both, now if the point particle is moving, we can tell the omega of this line joining. So let's say this is 2 and this is 1. So omega 2 1 means the angular velocity of 2 with respect to this one, the line joining 2 and 1. Omega 2 1 means the angular velocity of the line joining 2 and 1. So if it is moving in that direction, the line will also rotate in this way. So this gives omega to 1. And how do we find it? This omega is given by the velocity perpendicular to it. So it can be written as v to 1 perpendicular. The velocity of 2 with respect relative to 1, take its perpendicular component with this radius vector, and then divide by the radius. So component of this velocity perpendicular to this radius vector is omega to 1 perpendicular, and the distance between two is r divided by r. This gives the omega to 1, and the direction simply can be found by the direction. Here we have there is another quantity omega to 1 parallel. It is the radial velocity v radial. It changes the distance between two particles. Now here is what we had. Find the relative velocity of two particles and take the perpendicular component to the line joining both. And there you get the omega. Either this formula or use this formula. These two formula can give the omega. In general, for a particle, the omega is given by with respect to origin. So the one denotes origin, which is always at zero velocity. So we only need the velocity of 2 and component perpendicular to this RK, which is theta k. So the velocity of particle dot theta k gives the velocity divided by the opposite distance. It gives omega of any particle to with respect to origin, since it is always at zero velocity. And the radial velocity is given by v dot rk, only v dot rk. So it is a velocity. Now moving ahead, graphs. Some important graphs we need to know is AX graph. The area under the AX graph. What does it give? It gives the difference of velocity squares divided by 2, that is equal to area under the AX graph. How we get it? We know that in acceleration is equal to v dv by dx, and now this is equal to, when we take integration of dx and a, we get integration of v dv. This gives v square by 2. So there, this is how we get this relation. Area is equal to area under the curve is equal to v of 100 square minus v square divided by 2. And one important thing, if a particle is at, let's say, rest zero velocity and its acceleration is also zero, then the position of the particle will not change unless the acceleration changes from zero. So as long as the acceleration is zero, velocity will remain zero and particle will not move. Another graph is v square x graph. In this graph, the slope is important. Simply differentiate v square by dx, and it gives 2v dv by dx, which is equal to 2 times of acceleration. So 2 times of acceleration of particle is the slope of this graph. Now we have the equations of motions. First, how to write the equation of motions in Cartesian. First, write the position vectors xi cap y j cap, and then differentiate the position vector. We get velocity. The change in position is velocity, which can be written in this way. And dx by dt is vx, and dy by dt is vy. Notations. Acceleration is a change in velocity. Double differentiation of position vector with respect to time. This gives acceleration. Very simple equations for Cartesian system. Now, if you want 3D motion, you can add z-axis to like zk cap dz by dt k cap. Simple as that. Now, if you want to find average velocity, then you need to find the change in position vector. And if you want to find instantaneous velocity, then you need to find dr vector. Now, polar is a complicated thing. And this, the position vector is given by this. And differentiating velocity means dr vector by dt. It gives differentiating both are variables. If you take r cap as constant and differentiate r, we get dr by dt. This is the radius. The change in radius is given by dr by dt, not dr by dt. So this is the radius. This can be written as r vector is equal to r cap. So don't get confused. It can also be written as r cap, but this is actually the radius. So it is telling the distance only. So differentiating this, we get dr. dr is different. dr is different from dr. So change in radius is given by dr. डिस्टेंस का चेंज जो होगा उसको हम देंगे dr से. dr is equal to magnitude of dr vector change. So that's why we have added this sign here, not this. And now differentiating r cap, taking r as constant, radius as constant, we get omega theta cap. We derived this equation before, like dr cap by dt is equal to omega theta cap. Now the acceleration becomes more complicated. Differentiating on this gives these equations. Now one special thing is in circle we get acceleration is equal to, since radius doesn't change, this becomes 0. We get minus omega square r vector. This becomes minus omega square r vector plus, since this is v radial means the radius changing between the rate at which the radius changes, or distance between both origin and the particle changes. Since radius is constant, radial velocity will be 0. So this term becomes 0, and this becomes r alpha theta k. What is this? This is the tangential acceleration. R alpha theta k is the tangential acceleration, and this is the centripetal acceleration. Centripetal, and this is tangential. This is called Coriolis, and this is called linear acceleration. Now, to find velocity and acceleration, first we need to find equations for displacement. We need to choose an initial point and then we need to find the change in position vector with respect to time, and when we find the change in position we can divide by time taken, and it gives v average. And if we take a very small time difference, the velocity we get becomes v instantaneous. Similarly, the v instantaneous we found differentiating it gives dt. So first step is to find the position vector from initial point, or the displacement from position from initial point. First write the displacement vector equation, then differentiate with time. We will get this equation. For example, let's take one of these problems and solve it. First problem, let's say eh, there are two lines. One is moving with v1 velocity in this direction, one other is moving with v2 velocity in this direction, perpendiculars, and there is theta angle between them. Now to find the velocity of this point of intersections, we need to first write the equation of displacement of this position. So let's assume this is the initial position, this is our initial particle is initially at that position, and after t time this will move by a distance v to t, and this will move by a distance, this distance is v1t. Now we know the distance between these two, and this is the final position after t time. This was the initial position, this was the position after t time. We need to write the equation of this r vector, delta r vector. We can find this change in position using these quantities, and we will divide with time taken t, and we'll find the velocity of this intersection point. Simply with that. Now moving ahead, Snell's law for kinematics. For finding the fastest route, we can use the knowledge of light. Since light follows the fastest path, we can consider the path of light to find the fastest route. So if the scenario is similar to the cases we study in light, then we can apply this law, Snell's law. For example, if we are moving from one medium to another medium and we have different speeds of body in both medium, and if the particle is moving with high speed in this medium, then its angle is higher in this direction, and then only we can use Snell's law. Means this law is applicable only when this rule follows. If a particle is moving with higher velocity, then it should, if a particle is moving in this direction with higher velocity, then the angle should increase from theta 1, just like it happens in light case. And the formula we can use, sin theta 1 by v1 is equal to sin theta 2 by v2. Let's take a question to understand it. Let's say there is a road, and the car travels with 3v velocity in this road, and with a v velocity in the field, and he needs to reach this d distance. So the path taken by him would be like this, and it will make an angle theta here. we need to find the fastest route, the path which takes least time. So we know that if this is the fastest route, then this will be the fastest route when it is related, when it is traveling in the opposite path directions. Means if it moves in this way, it is the fastest path, then it is also the fastest path when it moves from this direction to this. Yep. If it goes reverse journey, then it also is the fastest path. So we will use light Cessna slow. This is the angle theta, and particle is moving with a v velocity, and it is making a 90-degree angle. It is very identical with case of light, where particle is moving with a theta angle with a small speed and then bends at, it is a critical angle case. The angle increases when speed increases. So we can say the sine 90 divided by velocity 3 is equal to sine theta divided by v, which gives 1.3 sine theta. So there we get sine theta value, and using sine theta we can find this is the angle it makes for the shortest path. So that's the solution for angle for the shortest journey. We don't even need a distance. If a particle moves from any point, it can start from this point, this point, this point. It will always bend at this point. No matter if it comes from infinity, it will bend at this point and go there. So remember that the path for one way is also for the same for reverse way. For the same fastest route are same for both coming both ways. And now there is one more type of problem. A walls, we have a cuboid shape, and and there is an insect that can only crawl on the walls. It cannot fly. So we are asked the shortest path between A and B. Since the object cannot fly, it cannot go diagonally, so the shortest path, it's not this, it must follow the walls. So we need to open up this box in many ways. Like if I open it this way, we will get this figure, and if I open the walls, like if I open it this way, means if I open it this way and put it down, it becomes this. And similarly we can open it in different ways and we get different paths. Now the shortest path we need to check by using Pythagoras theorem or any other thing, and we got this is the shortest path. So the particle moves from the wall behind and comes to this, it goes from this part to this and this. Simple questions. Now we have relative motions. I call this a chain rule. If you want to find the position vector of one with respect to t, put an intermediate position vector and then write this position vector with respect to this. Or you can use a longer way. For example, R1, I want to write R1 with respect to 2. I can write it as R1 vector with, let's say, R5 plus R5 vector with R4 plus r4 vector means this changes to this r4 vector with r3, and then plus r3 vector with r2. This becomes, so finally this become equal to r1 vector with 2. This is what I call chain. We can use this r1 is equal to r13 and 3 2. So finally v1 becomes relative to 2. Rain problems. In rain problems we need to point our umbrella in that direction from which rain is coming, relative to man, not relative to ground. So we need to find the relative velocity of rain with respect to man, and we will point our umbrella in direction parallel to that. So here is the velocity of rain with respect to ground, making an alpha angle with this vertical from positive x direction. So this is alpha, this is theta. Alpha and theta cap I took with positive with the direction of man moving. So this is velocity of rain with respect to ground, and this is velocity of man with respect to ground, and subtracted means this is equal to velocity of ground with respect to man. So I mean man was moving in this direction, vmg. So I took a negative of it and added, and I got this is vector of velocity of rain with respect to man. So I need to point my umbrella parallel to this, making theta angle with vertical, and the equation for this r and theta is equal to vrg sin alpha minus vgm divided by vrg cos alpha. Alpha is generally 0, not in all cases, but generally alpha is 0. So when it is 0, it becomes vrg minus vgm divided by vrg. And there is another equation, vrm cos theta is equal to vrg cos alpha, means the perpendicular distance here, vrm cos theta equals to vrg cos alpha, means the perpendicular distance here is same for both. That's what it means here. And the vertical line I chose is perpendicular to the velocity of man with respect to ground or any other point. So vertical line here is perpendicular to the man. That is the important thing we need to know here. If man is moving in that direction, then this formula is not applicable. It is only applicable if the man is moving perpendicular to the chosen vertical, or you can change your choice of vertical direction, then later you can transform it. River problems. River problems, simply we need to find minimum drift, minimum time. So minimum drift, we can remember this formula, v sin theta is equal to vr by vvr if vvr is greater, and if vr is greater then it becomes that denominator just reciprocal to make sin theta is smaller than or equal to, it cannot be greater than 1. Here vvr is making theta with this vertical line, and velocity of river is flowing that direction. Velocity of boat with respect to river is vbr, and the distance between both ends of river is l. So this gives me time to minimum time to cruise is L by VBR means if the boat is totally trying to move in this direction, then if it is using max velocity in this direction, then it will reach in minimum time. So this is so if you want to move fastest to this end, then you need to point all your velocity in that direction, because the river is always in that direction, so it won't help moving in that direction. So you need to point all your velocity in that direction for minimum time, but the particle will move something like that and reach there in minimum time. And for minimum drift, we have to move in any direction that makes theta with this direction for minimum drift to reduce this length. So for that we have the formula VBR. If VBR is greater, if VBR is greater, then we can simply make VBR sin theta is equal to VR, which means drift becomes zero since the component parallel to river is zero. And if boat is moving with a lesser velocity, then it cannot be zero, but it can be minimized, and the angle for that is this, and this theta is the angle made in opposite direction to flow. If river is flowing in that direction, theta is made with this direction opposite. This is positive for theta. There is one interesting question for river. For us to solve, let's try this. We will use Snell's law for that. A river is moving with let's say 2 v naught velocity, and a man is moving with v naught velocity, and on ground, this is ground, on ground the velocity of man is 3 v naught. Now we want to reach this P point just facing this direction, and we want to reach this point in minimum time to reach P. Now how to find this time and the path it takes? So for this we need to go into the frame of river. When we go into the frame of river, it becomes easy to apply Snell's law, because if we go and if we choose the ground frame, we cannot tell at which direction this body will move. It becomes very complex to tell the direction of this net velocity due to these two vectors, because you will have to make it move it at an angle theta with this vertical, and the resultant makes an angle alpha, and this becomes complex. So we will use relative velocity. Now we are moving. P point moves with a 2 v naught velocity with respect to river, and the particle gets a 2 v naught velocity here, and sorry, since v naught is the velocity of boat with respect to river, it will only have v naught velocity, becomes very simple, and it makes a theta angle. Now we know that for any case this particle will move and this to move since its velocity is less, or let's say even if its velocity was greater, let's say